Hey guys and gals, welcome back to 14.4. This is the integrated rate law. I believe we covered this in class, but just in case you need some extra help or work, we're going to run through it really fast. Basically, this section, 14.4, in the book, they go through all the derivation of these formulas, but we're not going to do that here. We're just going to kind of use the formulas and go from there. So we're going to jump right in. The integrated rate law. Remember, this is the dependence of concentration on time. So we're going to see how concentration is affected via time instead of the other way around, how time affects concentration. So if we look here, our first order integrated rate law, we have a formula, the natural log of a sub t over a sub o equals negative kt. The beautiful thing about this is this can be rearranged into a straight line plot or a formula for a straight line plot. And we've seen the formula we recognize is y equals mx plus b, and these line up with it perfectly. But the key is this is one of our formulas on our formula sheet, so we may have to use it. So let's look at this example right here. The reaction in example 14.3, which is a first order, has a rate constant of 0.00290 seconds to the negative 1. If the reaction is carried out at the same temperature and the initial concentration of SO2Cl2 is 0.0225 molar, what is the SO2Cl2 concentration after 865? So this becomes just a plug-in chug formula. All I've done right here is I have rearranged the above formula, this one right here, to isolate my natural logs because this is the one I'm going to be looking for, so we want to kind of leave it alone. So let's start plugging it in. As I said, we're going to leave natural log of a sub t alone because that's what we're looking for. We're looking for the concentration after 865 seconds. So we'll take minus natural log of a sub o, so our initial concentration, 0.0225, and that's equal to negative kt. So we're going to plug in our k, which is our rate constant, 0.000290, and we're going to multiply that by our time, which is 865. To save ourselves some time, I'm going to go ahead and move this natural log of 0.0225 to the other side. That way I can go ahead and just plug it all in my calculator at one time. And that will leave me with the natural log of a sub t is equal to all that fun stuff. So we're going to take negative 0.000290 times 865, and then we're going to add the natural log of 0.0225, which should give us negative 4.045. We're going to keep one more after that, 0451. And now we just have to find the natural log or the actual inverse of the natural log. So on our calculator, the best thing to hit is second and then hit that natural log button again. And we're going to use that answer that we got before. And now our new answer, our concentration of a sub t after 865 seconds is 0.0175. And that is molarity, or molar, because that's how much has went down the concentration in those 865 seconds. Awesome. So you can use that or do those plug-in chug type formulas anytime. So let's move on to a second order. So here's our second order one. Same premise. We still have a sub t, or the concentration of a sub t. So at concentration of A after some time. K is our rate constant still. T is our time. And we still start with 1 over A sub 0. So that's our initial concentration. Again, we can line this up with a straight line plot so we could graph this and see. Moving on to zero order. Same type of thing here. This one is our concentration of A sub T equals negative KT plus a sub 0. And that again lines up with the y equals mx plus b. Now the question is, how can this be used on the AP exam? I'm going to give you a couple of seconds to think of maybe one way that the integrated rate law could be used on the AP exam. Okay, that was definitely more than 1 second, but hopefully you had time to think about it. And yes, if you thought graphing, you are right. You may have to graph some data to figure out which one creates the straight line plot, so thus you can determine the rate law from that. And this is actually the lab we're going to do on Wednesday. We're going to graph our data and see which one creates the straight line plot so we know what the order is. Okay, kind of shifting gears just a little bit, we have our half-life of a reaction. Half-life, abbreviated T1/2, is the time required to reach 1/2 of the starting concentration. For a first-order reaction, that is T1/2 equals 0.693 over K. This is independent of concentration, so it doesn't matter how much we start with because it's always going to be that. And as you can see, there's no concentration in there. So our half-life is always constant, which means it does not change. So let's see if we can't just do a plug-and-chug problem here. Molecular iodine dissociates at 625 K with a first-order rate constant of 0.271 seconds to the negative 1. What is the half-life of this reaction? So here's our formula, T1/2 equals 0.693 over K. And all we need is our rate constant, which is given to us in the problem. So we've got 0.693 over 0.271. And if we keep 3 sig figs in our answer, that will be our answer. So I came up with 2.56 seconds. Very simple, as you can see. This one is also on our equation sheet. The next two are just here. We're not actually going to use them because, as I recall, I don't think they're on the formula sheet. So let's summarize some basic kinetic relationships. In fact, I'm going to let you read through those so we can just save some time here on our video. All right, so let's go ahead and knock out this little table right here. This is also given to you in your book, so if you want to use it, you can do that as well. So for a zero order reaction, we're just going to work across the whole thing. All right, so the rate law is rate equals K, because it's times the concentration of A to the 0. So yeah. Now our units of K, if you think about it, we've got rate, which is in molarity per second. We kind of look at it in that manner. Rate is molarity per second, and so K is going to also be in molarity per second, or molarity seconds to the negative 1. Okay? Our integrated rate law, this is what we learned how to do today, and that is where we're going to go right back up here to this formula, this guy right here, and we're going to transfer it down there. A sub t minus kt A sub O. So now, looking at this integrated rate law, our straight line plot, very simply, to see if it's a straight line, we're going to graph our concentration and see how it changes over time. So very simply, graph concentration versus time, and our slope is going to be negative, so our line should look something like that. Our half-life is T1/2 equals 0.693 over K. All right, so let's do the exact same thing down here for a first order. We've got rate equals K times our concentration, and that's to the first order or not. So if we break this guy down, our rate is in molarity per second. We've got K, and we've got molarity here. So one of our molarities cancels, and we're left with seconds to the -1. That's our unit on K. Our integrated rate law, this is where we use our natural log. Alright, so we've got the natural log of a sub t over a sub 0 equals negative kt. Again, our straight line plot, we've got the natural log of A, or the concentration of A, over our time, and our slope still negative. T1/2 is just right up here. Man, I screwed that up, didn't I? This T1/2 should be this guy here, 0.693 over K, because that's our first order. And for our 0 order, it is a tiny bit dependent. There it is. A sub 0 over 2K. All right, last but not least, write our rate law for second order. So we've got rate equals K times our concentration of A squared. Our label on this one, if we look here, we've got molarity per second equals K times molarity squared. So only one of our molarities will cancel. We'll still have one of them. And so we're going to be left with molarity -1 times seconds -1. That's our label. Our integrated rate law, this is where we have our fraction. 1 over a sub t is equal to positive kt plus 1 over a sub 0. So here, our straight line graph will be 1 over the concentration of A, t there, and it will be a positive slope because K in this case is positive. And last but not least, rolling back up there, we've got our T1/2 equals man, my equal sign is not working. 1 over concentration, well, K times the concentration of A sub 0. And there you have it. Thanks. See you next time.